So now that we know how to graph and deal with polar curves, we are going to learn to find area and arc length in polar coordinates. So the first question is, how would you find the area of a polar region bounded by some polar curve and two rays? So A equals theta and B equals theta, where the difference between B and A is between 0 and 2 pi. So that assumption means that the ray B is bigger than, greater angle than A. So we have some ray that's at an angle of A, some ray that's at an angle of B, and we have some polar thing that's doing some funky funk there. And we want to find the area of this region. And the first thing we could do is we could say divide this up into little bitty, very, very small pieces with small internal angles theta, and we can add up the angle of those little pieces. So what we need to be able to do is to find the area of a sector. And you can see that those little pieces are going to be kind of like a part of a circle, at least close enough-ish. There'll be a little bit of over-underestimate, but if we make smaller and smaller slices, we're going to get the actual area. So the area of a sector, so something like this, so part of a circle of radius r, angle theta, that area is given by 1/2 r squared times the angle theta. The only thing is that theta must be in radians. And here is why that is true. So you accept the fact that the area of a circle is pi r squared. So for a whole circle. Well, if you have just part of the circle spanned by theta, you've gone around theta out of 2 pi angles. That's the proportion of the circle you've traversed. So for example, if your theta was pi halves, you've gone around 1/4 of the circle. If you take pi halves divided by 2 pi, you get 1/4. So proportion of the circle. And the reason it's out of 2 pi is that there's 2 pi radians in the entire circle. And so this would equal, so that is the part you've gone around. So then the area of the sector, not the whole thing anymore, so that first one was an A for area of the sector, will be the part that you've gone around times the area of the whole thing, which you see those pi's cancel, giving us 1/2 r squared theta. That's not a formula I did in my geometry classes, but that's why it's true. So using that idea, the area of a single little bitty slice is going to be approximately equal to 1/2 r sub I squared delta theta, because delta theta will be a little bitty angle. And r sub I, well, we know that r is equal to f of theta, so that will be 1/2 f of theta sub I star, so some sample point squared delta theta. And to find the total area, well, that will be about equal to add up all those a sub i's. And then to get that area exactly, you take the number of pieces you have, the number of little divisions to infinity, and the area is exactly equal to the limit as n goes to infinity of that sum. And hopefully you haven't forgotten the calculus 1 that tells you that that becomes an integral. So we have the integral from your lower angle alpha to your higher angle beta, 1/2 f of theta squared d theta, or my personal preference as to how to write that is the integral from a to b, 1/2 r squared d theta. So that's how we're going to find the area of polar regions. And just like with Calc 1, it's really useful to first graph the polar region and then find the area. So 3 cosine of 2 theta. So first we'll sketch the curve in Cartesian coordinates. There's 2 pi, here's pi. This function will go through 2 cycles in 2 pi. So 1 cycle in pi, there's half pi, here's quarter pi, and here's 3/4 pi. Starts at 3, down to 0 by pi quarters, down to -3, and then back up, and the pattern repeats. This will actually be a 4-petal rose. So we start at 3, by pi quarters we're down to 0. This pi quarters to pi halves bit will be down here. That direction, that direction, that direction. So by pi, we're out at 3. 5 pi quarters back to 0. 3 pi halves. Had a radius of -3, back down to 0, etc. So I didn't try it this way, but you possibly could integrate just from 0 to 2 pi, and that might not be a problem. Or you could be really clever and use the fact that there's a lot of symmetry in this picture. So it's the only reason you can't see it is because of my lacking art skills. So this portion that I shaded right there, that is 1/8 of the whole area. So the total area could be given as 8 times the integral from 0 to pi quarters, 1/2 r squared d theta. Well, that 8 times 1/2 is 4. The r that we were given was 3 cosine of 2 theta. So that would be 9 cosine squared of 2 theta d theta, or 36 times the integral from 0 to pi quarters, cosine squared 2 theta. And you thought you could forget your half angle identities, but you cannot. This will be 36 integral 0 to pi quarters. Now cosine squared of 2 theta is 1/2 1 plus cosine of 4 theta d theta. That 36 times the 1/2 can make 18. And let's antidifferentiate. The antiderivative of 1 is theta. The antiderivative of cosine of 4 theta is 1/4 sine of 4 theta. So here we have 18 pi quarters plus 1/4 times sine of pi, minus 18 times 0 plus 1/4 sine of 0. And everything is 0 there except for the 18 times pi quarters, and 18 pi over 4 is equivalent to 9 pi over 2. All right, next let's find the area of the region that lies inside the curve 1 minus sine theta and outside the curve r equals 1. So first, the easy one to graph is r equals 1. It's a circle of radius 1. So there we go. All right, 1 minus sine theta. Well, first of all, minus sine theta will look like this. Start at 0, down to -1, up to 0, up to 1, down to 0. Then we add 1 to that. And there is the curve in the theta r Cartesian system. Well, this curve will start at an angle of 0, radius 1. By pi halves we're at 0, so we've done this kind of thing. By pi, we're back at 1. By 3 pi halves, we'll be at 2. And then by 2 pi, we're back at 0. So area inside first curve, outside second curve. So what we're looking for there is this area. And it was pretty easy to tell that the points of intersection were pi and 2 pi. You could have found that by setting 1 equal to 1 minus sine of theta. So 0 equals negative sine theta, and that would happen at these points. Also it happens at 0, which is why it's a little bit helpful to graph, but really we're spanning from this is the left to that is the point on the right. So this angle to this angle. And now you've got to figure out what is the outer curve. Well, in this case, outer greater, which one's a greater distance away from the origin. The one that's a greater distance away from the origin is the purple curve, the 1 minus sine of theta. So this area will be an integral from pi to 2 pi. 1/2 1 minus sine of theta, that quantity squared, minus the integral from pi to 2 pi of 1/2 times 1 squared d theta. And I'm going to combine those into one integral. So we'll pull out the 1/2, pi to 2 pi, and we will expand. So that'd be 1 minus 2 sine of theta plus sine squared of theta minus 1. Notice the 1's cancel. So we have 1/2 integral from pi to 2 pi, negative 2 sine theta. We have to express sine squared theta using our double angled identities. That's 1/2 1 minus cosine of 2 theta d theta. So here we go. 1/2 integral pi to 2 pi, negative 2 sine theta plus 1/2 minus 1/2 cosine 2 theta. And now we can antidifferentiate. Well, the antiderivative of negative 2 sine theta is 2 cosine theta. Antiderivative of 1/2 is 1/2 theta. The antiderivative of cosine of 2 theta is 1/2 sine 2 theta, multiplied by the other 1/2 gives us 1/4. So we'll have 1/2 times 2 cosine 2 pi plus 1/2 times 2 pi minus 1/4 sine of 4 pi minus 1/2 times 2 cosine pi plus 1/2 pi minus 1/4 sine of 2 pi. And that will be 1/2 times 2 plus pi minus 1 times negative 2 plus pi over 2, which will be the same thing as 1/2 times 4 plus pi halves, or 2 plus pi quarters. It's really easy, at least for me, to get lost in the arithmetic, so I would suggest probably not skipping too many steps and being a little bit careful. And the reason that the angles had to go from pi to 2 pi is if you would have used 0 to say pi, that's when this part of the curve is spanned for those angles. So you have to go from when does this start spanning to when does it end spanning. So for example, even though 0 works in that equation, it's not a point that you use for your bounds. Now it's also possible that you don't have to use the whole outside-inside curve, and you can use some symmetry to make your life easier, and this will be an example of that. So we have the curves 1 plus cosine of theta and 1 minus cosine of theta. So for 1 plus cosine theta, so cosine theta would look like this. Adding 1 to it moves it up. It's going to produce one of those heart-shaped things. So we start at 2. By pi halves we're at 1. By pi we're at 0. So we've done this kind of business. By 3 pi halves we're back at 1. And by 2 pi we're back at 2. So ish approximately looks like that. Whoa, whoops. White out. Okay, now the second curve, which is 1 minus cosine of theta, well, that would have been flipped upside down, at least initially, like this, and then moved up 1. I like it when there's no negative radii. So this one starts at the origin, and by pi halves we're up at 1. By pi we're at 2. By 3 pi halves we're back down to 1, and by 2 pi we're back at 0 again. So we're looking for the area that lies inside these curves. So inside there and inside there. And you can do this lots of ways, but I think the easiest way is to find the area of this piece of the blue curve. And that piece of the blue curve was spanned from 0 to pi halves. And if you believe your picture, you can see that the area between these curves will be exactly 4 of those little half football shaped things. So the area between these curves will be 4 times the area of one individual piece. And the area of one individual piece, the ray that begins is an angle of 0, ends at an angle of pi halves, and we'll have 1/2 r squared d theta. So 4 times the 1/2 makes 2. And the r is the 1 minus cosine of theta, that quantity squared. So it'll be 2 times the integral from 0 to pi halves, 1 minus 2 cosine of theta plus cosine squared theta. And if you didn't know your half angle, double angle identities, you're going to have to at the end of this lesson because they come up so often. So 1 minus 2 cosine of theta plus 1/2, 1 plus cosine of 2 theta. And just combining like terms before I go off and anti-differentiate, that 1 plus that 1/2 will be 3/2. Okay, so the antiderivative of 3/2 will be 3/2 theta. The antiderivative of 2 cosine theta will be minus 2 sine of theta, and then we'll have plus 1/4 sine of 2 theta from 0 to pi halves. And now let's input our bounds. Just give me a little bit more space. And also before I do that, I'm going to distribute that 2. So I have 3 theta minus 4 sine of theta plus a 1/2 sine of 2 theta from 0 to pi halves. Okay, so this will be 3 pi halves minus 4 times sine of pi halves. Plus 1/2 sine of pi, and then minus what looks like will be 0. So that's 3 pi halves minus 4, and that's definitely wrong. The next thing we're going to discuss are points of intersection of polar graphs. So you can find the points of intersection of polar graphs by, say, setting the two equations equal to each other, but it can be a bit tricky because the representation of points is not unique. So let's write that down. So the fact that a single point has many, officially infinitely many, representations can make it difficult to find points of intersection. What you can think about is you can think about these curves, instead of theta being angle, you can think about, say, theta being t for time. And what might happen is that even though two curves intersect someplace, like say at those points, they might never intersect there at the same time. Like this could be the path of one planet and another, and they just happen to say that they were exactly equal and they went at the exact same rates, and one was here and one was here. They're never going to actually hit each other, even though the two curves do actually intersect. And so, for example, we have, at least in one example, we're going to graph 1 plus sine theta, and we're going to graph the curve 3 sine of theta. These intersect at the origin, but never at the same theta. So that's still, the origin is still a point of intersection, it's just that they don't happen to be there at the exact same moment. And the point here is that you really have to graph the curves to be sure you got them all. And so let's do that. So find the points of intersection of the curve 1 minus 2 cosine of theta and r equals 1. So r equals 1 is easy. Let's get that over with and graph it. So there's r equals 1. 1 minus 2 cosine theta. There's 2 pi. Here's pi. Negative 2, positive 2, theta, r. All right, well, that would negative 2 cosine theta. We begin at negative 2, up to 0, up to 2, down to 0, down to negative 2. That's the unshifted curve. Shifter up 1. All of a sudden that at 3, that's at 1, that's at negative 1. Oh man, we start off negative, how tricky. So angle 0, radius negative 1. So we appear to be angle 0, radius negative 1 is that point there. And that will be when cosine is 1/2, which is at pi thirds. So all these dots here are going to reflect over there. So right now we're at this point on the curve, and as we increase to pi halves, our radius has increased to 1. So there's the part of the curve. By pi, we're out at 3. By 3 pi halves, we're back at 1. And got a little bit of time until you go back down to 0, and then that loop finishes off. So this should be a little bit more circular, it's just my inability to draw. So you'll have to excuse my inability to draw. And now let's find the points of intersection. So it appears from here we have one point right there. So that would be the point r is 1, theta is pi. And these 2 points here where the r is 1 and the theta is pi halves, and the r is 1 and the theta is 3 pi halves. And those you could just extract from the picture. Just remember that they're given in r theta form. You could also solve them by setting the two equations equal to each other, and let's just examine what happens when you do that. If you set 1 equal to 1 minus 2 cosine of theta, that's 0 equals negative 2 cosine of theta, or cosine theta equals 0. And cosine of theta is 0 at theta equals pi halves and 3 pi halves, which are two of the points we found, but this method misses the point 1 pi. And that's because while those two curves intersect there, they're never there at the same theta value. All right, here's another example. So r equals 2 cosine of 2 theta, and theta is 1. So here's theta equals 1. 2 cosine of 2 theta, well, that will be a cosine curve that goes twice as fast as normal, so 2 cycles in 2 pi instead of 1. Starts off at 2, down to 0 by pi quarters. There we go. 3 pi halves, 5 pi quarters. Okay. So at an angle of 0, we're going to start off at 2. By pi quarters, we're down to 0. Pi halves, negative 2, does this part, back to 0. By pi, we're at 2. 5 pi quarters, we're back to 0. 3 pi halves, we're at negative 2, so that's up here. Back down to 0, and finish. And it's pretty obvious from the picture, although your ability to graph it perfectly will determine if you can see where they are, that there are 8 points of intersection. 1, 2, 3, 4, 5, 6, 7, 8. And let's try to find them from the equations. So let's set, and that shouldn't have said theta equals 1, it should have said r equals 1. So let's solve 1 equals 2 cosine of 2 theta. That's a half equals cosine of 2 theta. And ask yourself, when does cosine of something equal to 1/2? Well, that will happen if that something had been equal to pi thirds or 5 pi thirds. And because this function is oscillating twice as fast, we have to actually go around the unit circle twice to get all of them. The next point would be 7 pi thirds and 5 pi thirds plus another 2 pi would have been 5 pi thirds plus 6 pi thirds, or 11 pi thirds. And that gives us theta equals pi 6, 5 pi 6, 7 pi 6, and 11 pi 6. And my picture was far from perfect, but that appears to be this point, this point, this point, and that point. All of the 6. And the question is, well, how the heck do you get the others? And here is the tricky thing. R equals 1 is a circle of radius 1. So is r equals negative 1. It's just that the circle is going to be traced in the opposite direction. So the other thing that you can solve to find the rest of them is negative 1 equals 2 cosine of 2 theta. So it'd be negative 1/2 equals cosine of 2 theta. And that will be true if 2 theta is equal to, well, 2 pi thirds for 1. 4 pi thirds for another, and you've got to go around the unit circle twice because this oscillated twice. So that would be 2 pi thirds plus 2 pi would be 8 pi thirds, and 4 pi thirds plus 2 pi would have been 10 pi thirds. So in that case, you get theta equals 2 pi thirds, 2 pi thirds, 4 pi thirds, and 5 pi thirds. And from your picture, I think you should believe that that seems right, because this appears to be about pi thirds. That appears to be about 2 pi thirds. There's about 4 pi thirds and 5 pi thirds. So just be aware that graphing the curve, you should observe how many points of intersection they are, and you have to find some method of finding all of them. If they're easy to see from the picture, you can just pull them from the picture, but I think easy to see means that they're on an axis, and obviously so. And the final topic we'll discuss for polar curves is how might you find the length? Well, the length of a parameterized curve we found was the integral from alpha to beta square root of dx dt squared plus dy dt squared dt. And in the case of polar curves, we have x equals r cosine of theta and y equals r sine of theta. So we are going to use that parameterization, and we're going to simplify it, and it's going to simplify quite a lot. So I'm going to leave the square root sign and the integral off for now because it's just going to be messy. So we're simplifying dx d theta squared plus dy d theta squared, which will be simplifying this expression under the root sign. Now dx d theta will be dr d theta cosine theta minus r sine theta, that whole quantity squared. dy d theta will be dr d theta sine theta plus r cosine theta, the whole quantity squared. Holy moly. All right, write really small. Okay, squaring the first expression, we're going to have dr d theta squared cosine squared theta minus twice r cosine theta sine theta dr d theta, and then lastly plus r squared sine squared theta. That's just the first expression. Plus the second one will be very similar, dr d theta squared sine squared theta. Now this time plus 2r cosine theta sine theta dr d theta, and then plus r squared cosine squared theta. And thankfully, at least something cancels. We have dr d theta, the quantity squared, times cosine squared theta. We have a dr d theta squared times sine squared theta. This has canceled with this. We also have a plus r squared sine squared theta and a plus r squared cosine squared theta. And I chose to group those that way on purpose because now I'm going to take the greatest common factors out of these two groups. Dr d theta quantity squared times cosine squared theta plus sine squared theta plus r squared times sine squared theta plus cosine squared theta. So both cosine squared plus cosine squared theta plus sine squared theta and sine squared theta plus cosine squared theta, those are both equal to 1. So in the case of a polar curve, that stuff under the radical simplifies to dr d theta squared plus r squared. So put a big box around this. The length of the curve is the integral from your alpha to your beta, or a to b, angle to angle, of the square root of dr d theta squared plus r squared d theta. Bam. All right, let's do that to find the exact length of this curve. R is 2 cosine theta for theta between 0 and 2 pi. So this length is the integral from a to b square root r squared plus dr d theta squared d theta. So we're told that the angles are between 0 and pi. Well, r will be 4 cosine squared theta, and since dr d theta is negative 2 sine theta, that squared will be 4 sine squared theta. Take out the greatest common factor of 4, square root it, we get 2 integral 0 to pi root cosine squared theta plus sine squared theta. Your favorite trigonometric identity, which is just 1. So 2 integral 0 to pi 1 d theta. Well, the antiderivative of 1 is just theta from 0 to pi, so this is 2 pi. And if you were to graph this curve, you would have found that it is a circle centered at the point 1, 0 with radius equal to 1. So its circumference should have been 2 pi r, or 2 pi, so that does jive. So let's set up, but don't solve, an integral that gives the length of the choroid r equals 1 plus sine theta. So in this case, dr d theta is cosine of theta, and the length will be the integral from a to b root r squared plus dr d theta squared d theta. At some point in time, we graphed this curve, and the whole curve is traced from 0 to 2 pi, so the bounds are 0 to 2 pi. If you're uncertain what the bounds should be, you should graph the curve and figure out at what value of theta, so start with theta equals 0. From 0 to what value of theta does it take to have the whole curve traced? So this will be an integral from 0 to 2 pi. R squared is 1 plus sine of theta, quantity squared, plus cosine squared theta. And we're not going to solve this all the way, but we can at least simplify it. 1 plus 2 sine theta plus cosine squared theta plus sine squared theta. Sorry for a second there, I just did the wrong order. Doesn't matter though. Well, cosine squared plus sine squared is 1, so this is the same thing as the integral from 0 to 2 pi root 2 plus 2 sine of theta d theta. And this works out to be 8, but it's quite tricky to do that. So for now, I think just the fact that you can set it up is good enough, and I'll give you ones that don't involve super trickiness.